Why is the Einstein Telescope using crystalline silicon for its mirrors instead of fused silica like literally everywhere else? So, as I mentioned in the overview video of the Einstein Telescope, it is a third-generational gravitational wave detector, which means a whole bunch of new technology, and in this case includes the mirrors. So, usually most interferometers use mirrors that are made of fused silica, which is known to be very good for optics and is usually the material that is used for most optics. That's because fused silica is known to be easy to work with. You can easily make optics with it that without a lot of impurities that would then mess up the path of a laser, as well as it's known to be able to be easily polished and coated to have like the different special coatings needed for mirrors, as well as it doesn't degrade very easily. However, one of the issues with fused silica is one of the other new technological additions, which is the cryogenic system. They're adding cryogenics to reduce thermal noise, which is something that can be very annoying when dealing with the signals, but fused silica doesn't do too hot in cryogenics, pun intended. Specifically, the issue comes in with Brownian thermal noise, which is connected to the mechanical Q factor of a material. The mechanical Q factor is a value of how much energy is lost in an oscillation cycle. And when there is a lower mechanical Q factor, there is a higher amount of energy being dissipated, which also means when there is a lower mechanical Q factor, there is a higher amount of a Brownian thermal noise, which can really mess up a gravitational wave signal. At room temperature, which is about 123 degrees Kelvin, both fused silicon and crystalline silicon have decently high mechanical Q factors, meaning there isn't a lot of thermal noise. And fused silica is actually really good at that temperature. It's why in all the other interferometers are one of the reasons why fused silica is used. But when you start getting to the cryogenic temperatures as low as below like 20K, the mechanical Q factor of the fused silica plummets, so there is a whole bunch of Brownian thermal noise. However, crystalline silicon actually gets better. It gets a higher mechanical Q factor, so it makes it that the Brownian thermal noise is minimized. There's another variable that is also important to consider, and that is the coefficient of thermal expansion. The coefficient of thermal expansion is another value, and it is how much an object will change its shape at a certain temperature. And for crystalline silicon, there are two temperatures where this coefficient is 0, meaning that it really won't change its shape. And these happen to be room temperature, 123 degrees K, or around 20K, which is the temperature that they're aiming for the cryogenics. And so this makes it that there's not as many issues with the mirrors actually changing shape, because that could really mess up a signal. There's also a side effect to changing this material, and that is you have to change the wavelength of the laser that you are using. So the usual wavelength that is used is 1064 nanometers, because fused silica is transparent at that wavelength. However, crystalline silicon is opaque at that wavelength, which you don't want to use when you're having a bunch of lenses. Opaque lenses don't really help you. And so crystalline silicon is transparent instead at wavelengths above 1200 nanometers. And so the wavelength that was chosen for the laser is 1550 nanometers, since it's easier to find commercial lasers at that wavelength since it's used for telecommunications. And that is a number that I have become increasingly familiar with when I was in the laser corner, because I had to make so many labels with that number that needed to be labeled of which laser it was for. So that was a number that I was constantly typing out.